You've probably gazed at one, but you can never actually reach it. A rainbow isn't some physical object anchored in the sky, but a massive optical illusion. Because of the intricate dance between light and water, no two people will ever see the exact same rainbow. Each person views a different set of raindrops at a slightly different angle, because you and a friend standing right next to you have a different anti-solar point and a unique horizon. You're each witnessing a different phenomenon. It sounds like a magic trick, but it's the rigorous truth of physics. Today, we're going to uncover the mystery of why this happens, why the light bends at a very specific angle, and why we've been told for centuries that there are exactly 7 colors in that shimmering arc. Picture a rainy afternoon where the air is thick, heavy with moisture. The sun is finally breaking through the dark, bruised clouds, and the atmosphere is crowded with millions of floating water droplets. It's a perfect storm of conditions. To witness a rainbow, you need both rain and sun to occur simultaneously. This is the non-negotiable requirement. As the observer, you must stand with the sun directly behind you, looking straight into the falling rain. When these two elements, the sun and the raindrops, converge at the same point in the air, the rainbow is born. Wait, let's look closer at the air itself. There's something happening inside those tiny spheres of water that defies a simple explanation. For centuries, natural philosophers assumed the rainbow was a mirror-like property of the entire cloud. Aristotle, for instance, argued that rays reflected off the cloud's surface, similar to light bouncing off a polished basin. It was a logical error that persisted for ages. But then, a fundamental shift occurred in the early 1300s. Theodoric of Freiburg realized that Aristotle's whole cloud model couldn't explain the precise angles observed in nature. He set aside the sky and turned to a flask of water. By treating a single spherical droplet as a lens, he successfully modeled the refraction and reflection of sunlight. Theodoric proved that the rainbow is not a property of the cloud, but a consequence of light's interaction. With an individual raindrop, think of a light ray as a tiny, high-speed traveler. Because the sun is so distant, these rays reach raindrops essentially parallel to each other. Now consider what happens when that sunlight strikes a spherical water droplet. Some of the light simply bounces off the front surface, but the rest is transmitted into the heart of the sphere. As it enters, the speed of light changes. Light slows down and refracts, meaning it bends, when it enters a dense medium like glass or water. This happens because in a medium, light pushes charges back and forth, causing them to vibrate at the frequency of the light. This phase kick decreases the wavelength of radiation in the new medium, which in turn slows the light down. To quantify this, physicists use the refractive index, the speed of light in a vacuum, divided by its speed in a medium. For water, that refractive index is 1.33, roughly a third slower than in a vacuum, compared to around 1.5 for glass. Now, here is the magic of these microscopic prisms. As the light enters the raindrop, it bends at separate angles, splitting into different rays. This initial refraction causes the white sunlight to splinter into its component colors. The light then travels through the droplet and reflects off the back interior surface before exiting. It bounces off the back, is refracted once more as it leaves the water, and finally the human eye captures these bent light rays. This precise sequence of refraction and reflection transforms simple raindrops into a multicolored arc. Why does the light not just scatter in every direction like a shattered mirror? Well, it's because of a phenomenon called acoustic. Acoustic is simply a concentration of light rays. In a sphere of water, this concentration happens at very specific angles. For red light, the maximum scattering angle occurs at 42 degrees below the horizontal. Green light, however, follows a slightly different path, peaking at around 41 degrees. Blue and violet light approach a maximum scattering angle of 40 degrees. This happens because higher frequency light, like blue, the charges vibrate with greater amplitude, leading to a larger phase kick and more bending. The magic number here is 7/8 the radius of the sphere. That's the exact point of reflection on the back of the sphere required to hit these maximums. Consequently, a primary rainbow is formed when the angle from the sun to the raindrop to the observer's eye is between 40 and 42 degrees. This narrow window, a sliver of just 2 degrees, is the only reason we see a clear, defined arc instead of a blurred mess of white light. But here is where the history gets a bit strange. We've always been told there are exactly 7 colors in a rainbow: red, orange, yellow, green, blue, indigo, and violet. It feels like a mathematical law of nature, doesn't it? But in reality, the spectrum of light is a continuous, seamless blend. There are no hard lines or borders between these hues. They simply bleed into one another in an infinite gradient. So why did we settle on 7? This wasn't a discovery of a physical boundary, but rather a decision based on a historical and mystical belief in the number 7. Isaac Newton, the man who first mapped the spectrum, was obsessed with the harmony of the universe. He noticed that the 7 colors of the rainbow matched the 7 notes on a musical scale. To him, this wasn't a coincidence. It was proof of a cosmic connection between light and sound. He essentially forced the spectrum to fit a musical octave, adding indigo to the list just to make the count reach 7. When you look at a rainbow now, you aren't seeing 7 distinct stripes of paint. You're seeing a smooth, unbroken flow of energy, and we simply use those 7 names to make sense of the chaos. Now, let's shift our perspective. If you've ever wondered why the rainbow looks like an arch, the truth is actually more surprising. A rainbow is actually a full circle. We usually see it as a semicircle because we're grounded, and the horizon simply cuts off the bottom half of the ring. However, if you were in an aircraft or standing on a high peak, you could see circular rainbows where the complete ring of color is visible. The secret is in the geometry. The center of the rainbow arch is on a line passing from the sun through the back of the observer's head. This means your own shadow is the center, the anti-solar point, which is always opposite the sun. Because of this specific alignment, the primary rainbow only appears when the sun is at a certain height. In fact, rainbows are not visible from the ground when the sun is more than 42 degrees above the horizon. The whole thing is a perfect personal geometry of light and your eye. It's wild to think that this whole process happens in a fraction of a second. When we look up at that massive arc in the sky, we're actually seeing the combined effort of millions of droplets, each one acting as a tiny, precise optical machine. A single raindrop creates a cone of light with a white center and a colored ring around the outside. It's this specific geometry, this tiny single drop event, that repeats across the sky, creating the illusion of a solid object. We're simply catching the colored ring from millions of different drops at the time, and our brain interprets that as a continuous, shimmering arc. The scale shift is truly staggering. From the invisible wiggling of charges in a microscopic sphere of water to a colorful spectral bridge that spans the entire horizon. It's like looking at a galaxy through a microscope. Sometimes the sky behaves even more strangely. If you've ever noticed the area under a rainbow is brighter, It's because raindrops beneath it reflect all colors of light back to the observer. But what happens when light reflects twice inside the raindrop instead of once? That's when we see a double rainbow. In the secondary rainbow, the spectrum is reversed. The red is on the intersection and the violet is on the outside. Between the primary and secondary rainbows, there is a dark sky region known as Alexander's dark band. This dark band exists because no light reflected once or twice comes out at that specific angle. Now, a curious detail, rainbow light is polarized perpendicular to the plane of reflection because light parallel to the plane is transmitted at Brewster's angle. This means polarized sunglasses can make a rainbow disappear or appear brighter, depending on the filter orientation. And for the truly observant, third and fourth order rainbows exist, but they are so faint they're only visible when looking in the direction of the sun. If you look at the inner edge of the primary rainbow, you might spot supernumerary rainbows. These are faint, light, and dark bands caused by the constructive and destructive interference of light rays. For these supernumerary bows to appear, the raindrops must be incredibly small, around tenths of a millimeter in diameter, about the size of a fine mist particle. This happens when the droplet size distribution is narrow, making the bands appear widely spaced. Beyond these, there are glories, also known as Brocken bows. These are small circles of color, only 2 to 4 degrees wide, which occur when light interferes in droplets that are just tenths of a millimeter. You might see these in a cloud bow or fog bow, where the mist is so fine that the physics of light bends into something entirely different. It makes you wonder what other patterns are hidden in the air, waiting for the right angle of light to reveal them. But ultimately, a rainbow is not a destination or a physical object you can chase. It's a relationship, a precise geometric alignment between the sun, a million tiny spheres of water, and your own eye. From the 42-degree angle that concentrates the light to the anti-solar point anchored to your own shadow, the entire experience is personal. Even the 7 colors we name are a legacy of Newton's desire for musical harmony, masking a seamless, unbroken gradient of energy. Because each person stands in a different spot, possessing their own unique horizon and their own specific anti-solar point, no two people ever see the same rainbow. You're witnessing a version of the sky that exists only for you, a unique optical signature written in light and water. What other invisible geometries are currently shaping the world around us simply because of where we happen to stand?